Hello, I'm Kirk Weiler, and this is Common Core Algebra 2 by eMath Instruction. Today, we'll be looking at Unit number 13, Lesson number 7, the difference in sample means. So, we've been doing inferential statistics, and we've been doing statistical simulation for the last two lessons. Today, we're going to conclude our work in inferential statistics and statistical simulation by looking at classical experiments. But let's take a look at what that even means. How a classic experiment works. In a classic experiment, two or more treatment groups are randomly created, then subjected to different treatments. The question then becomes to determine if the variability between the treatment groups is due to the treatments themselves or other sources of variability. All right? So again, this is where randomization is important. This is where the analysis of variation and variability is important, right? We're going to be dividing up subjects into two or more groups, treating them differently, seeing how they respond, and then understanding why the variability occurred. All right? So let's jump into this exploration. Okay, exercise number 1. Suppose 50 people were chosen to try out a new diet pill. Okay. The people are randomly divided into two groups. One is given the pill, while the other is given a placebo. A placebo is a pill that is designed to look like the real one, but with no medicine in it. There are two main ways variability can be introduced. Discuss each. All right. So pause and think about these, and if you need to, go back to look at our types of variability from the lesson 1 in this unit. All right. Well, induced. Okay. So the induced variability, this variability will occur because of the medicine used to lose weight. Or at least we hope that it'll occur, right? If we're the people that are making this drug. So there's going to be, this is going to be between the two groups. So, we expect, we don't know, but we expect that we'll get more weight loss in the group that took the pill than the group that didn't take the pill. But then we have natural variability. This variability will occur because different people lose different amounts of weight. All right, and this could even happen within the groups, right? So even in the group that takes the weight loss pill, right? Even in that group, right? What's going to happen is some people will lose more weight, some people will lose less weight, some people might not lose any weight at all, right? And it's not because they took the pill or didn't take the pill, but simply because some people will lose weight quicker than other people due to their metabolism, due to how much they exercise, etc., etc. All right? The primary goal of statistics, especially in this situation, is to try to figure out how much of the variability was induced and how much of the variability was natural. Because, of course, if a lot of the variability was due to the induced variability, then from the drug company's perspective, that's a good thing. They can say, yeah, on average, people who took the drug lost this much weight and people who didn't lost this much weight. And wow, isn't that great? They lost more weight by taking this drug, right? But of course, if the variability is just due to natural things, well then you can't really claim that it was due to the drug, that it was due to the treatment. So let's take a look at how this continues to play out. All right, we're going to be sticking with one large example for the rest of the lesson. Okay, we've got a seed company and it's trying to determine the effect of synthetic nutrients versus organic nutrients on the growth rate of corn plants. Everybody likes buying stuff that says organic, but there's a reason why certain things aren't organic. All right. So they select 40 seeds at random, 40 seeds, and they randomly distribute them. Remember, this is randomization. So they randomly distribute them. So 20 go to one group and 20 go to another group. The seeds in group 1 are given the organic nutrients. So group 1 is the organic nutrients, group 1 organic, and group 2 are given the synthetic nutrients. After 3 weeks, each plant's growth is measured in centimeters. So here they are. This is how much each plant grew in centimeters, and they're arranged in ascending order. The first thing says, enter these two lists on your calculator, state the mean of each, then create a box plot of each using the grid below. You may want to summarize the information you need under each heading. All right. Well, first things first, I'm gonna put organic here, and I'm gonna put synthetic here. Now, I don't want to take up your time by entering the data and running through all the buttons. You should be very familiar now with how to enter data on your calculator and how to get everything that you need to create a box plot. All right. So here are the results. For group 1, the organic, the mean was 15.15 centimeters. All right. The first quartile, which we'll need to create the box plot, was 12. The median, which we'll also need to create the box plot, was 15. And Q3 was 18. All right. So its box plot would look like this, right? We'd have a line at the min, which is 6, a line at the maximum, which is 25, a line at Q1, which is 12, a line at Q3, which is 18, and a line at the median, which is 15. So it would look something like this. All right, some seeds grow better than others. That's the natural variability. Okay, group 2, it had a mean of 17.45 centimeters. All right, it had a Q1 equal to 15, a median equal to 18. I'll put Q3 over here was 20. And I'm going to actually put its box plot below the number line. So it had a minimum of 9, it had a maximum of 28, it had a Q1 of 15, it had a median of 18, a Q3 of 20. So it looks something like this. All right. So what those box plots do is they give us a good sense for how things overlap, what the spread of the data is. And really, the two box plots look very similar. It just seems like the synthetic one has been moved up by about 3 centimeters. About. All right? Pause the video now and write down anything you need to. Okay. I'm going to clear out the text. Now, right here, I've got everything summarized from that last graph. I even don't have the whiskers on the box plot. So exercise 3 says, let's look at the descriptive statistics. All of this, everything you see on your screen right now, are descriptive statistics. Okay? What does the data suggest? And does it give a clear indication that one treatment resulted in greater plant growth? All right. Well, the descriptive statistics suggest the seeds in group 2, which was the synthetic, group 2 grew more than in group 1. Should have capitalized that. In group 1. But does it give a clear indication? It does not, in my opinion, give a clear indication because there were seeds in group 1 that grew more than seeds in group 2. Right? I mean, look, think about it. Right? There are tons of them in here. There are many seeds in group 1 that grew more than many seeds in group 2. In fact, the peak seed in group 1, right? The one that grew 25 centimeters is bigger. That thing is bigger than more than 75% of the seeds in group 2. So it would be too simplistic to just simply say, no, we've proven it. Given this information, we know beyond a shadow of a doubt that the synthetic fertilizer, the synthetic nutrient, is going to give better plant growth than the organic one. We can't say that yet, all right? But we're going to run a simulation in just a moment that's going to help us get closer to that conclusion. All right, write down anything you need to, and then we'll do the simulation. All right. Now, ultimately, what we're really trying to do now is we're trying to figure out how much of the difference in the sample means could be attributed to the natural variability and how much is attributable to the treatment variability or the induced variability. All right? So that's what we're going to be looking at in this final simulation. The first thing I want to do is take a look at what's called the observed difference in the sample means. Now remember, our two sample means, x bar 1, the one with the organic, was 15.15 centimeters, and x bar 2, the one with the synthetic, was 17.45 centimeters. So the difference between the two, and we could do the difference in either of the two ways, it really wouldn't make any difference, but our simulator is going to do it in this order, so we want to keep to the same order, was 2.30 centimeters. In other words, the mean growth in group 2 was 2.3 centimeters greater than the mean growth in group 1. Now again, the question is, well, was that due to the induced variability, or was that due to just natural variability? Well, here's how we can simulate that, and this is really cool. So before I break out of this and jump into the simulator, I want you to really understand what the simulator is going to do. It's going to take these two sets of data, all right, and it's going to scramble them together. It's just going to throw them all together. And then it's going to randomly assign them back to two groups that are the same size, and it's going to calculate the means. And then it's going to subtract them, and it's going to calculate a difference, just like we did here. And then it's going to do it again and again and again and again. So what it's really doing is it's saying, forget about the treatment at all. I'm just going to randomly assign these things to groups of, I think they were groups of 20? Yeah, they were groups of 20. So I'm just going to take these 40 growths and randomly assign them to groups of 20. All right? And what that's going to do is it's going to simulate a bunch of natural variability. Okay? And we're going to ask a very simple question. How often, when all we're looking at is natural variability, how often does a difference of 2.3 centimeters come up? If it comes up fairly frequently, well then we can say, well then probably that variability in those two means was due to just natural variability. And if it doesn't come up almost at all, then maybe we can say it's due to induced variability. All right? So what I'm going to do is I'm going to clear this text out. I'll write it down again when we pop back in here. But let's run the simulation. Now, in order to run this simulation, I have to have the data already in my calculator, and it's in there. It doesn't have to be in ascending order or anything like that, but all the data is in there. And now what I'm going to do is I'm going to go into my program, and I'm going to use what's called mean compare. All right? All right. And all it asks me is the number of simulations. That is it. So we're going to do this 100 times. And again, remember what it's going to do. It's going to take these two lists and it's going to scramble them together and throw them into two more lists. It's going to calculate their means, subtract, and get a difference of means. Okay? Sometimes that subtraction is going to be negative. Sometimes it's going to be positive. It's always going to do the mean of L2 minus the mean of L1. All right? Now, these simulations definitely take some time because it takes time to throw the data out there, scramble them up, and then throw them back into random groups. So yet again, we're going to pause and clip that video so you don't have to watch this entire simulation. Okay, well, we're getting there. We're almost through our 100 simulations. And then we're going to see about those differences in sample means. All right, they're there. Let's peruse the data a little bit. Let's just kind of see what it looks like before we do what we're supposed to do in letter B. All right. So my differences in sample means are in L3. Okay. My data is still in L1 and L2. I didn't want to get rid of it. But look, here we have a difference of sample means of negative 4.6. Right? So in one sample, we scrambled these things up, and sort of the treatment group number 1 had a much higher sample mean in that case. Remember, we're doing L2 minus L1, so any kind of negative values here indicate that L1 ended up having a larger mean than L2. On the opposite spectrum, all right, we look like we have a difference, largest difference of 3. All right, so there's there's a variety of different differences that occur here when we randomly scramble up these groups. Now, one way to kind of get a sense for this is to actually look at a histogram to look at a distribution of these. Now, to create histograms on the graphing calculator is actually a little bit of a challenge. Okay, I won't lie to you there. We've got a maximum of 3 and a minimum of negative 4.6. So in order to make a histogram, what I have to do is I have to go in and turn on the histogram. So I have to actually turn on my chart. I have to go down and grab histogram. All right. I have to go down and grab the histogram. It's not seeming to grab it. There we go. All right. I actually have to change my list not from L1 but to L3. My frequency is 1. Yep. Then I have to make a window. Let's see, my lowest one was negative 4.6, so I'm going to go negative 5. My highest one was actually 3, but I think I'm going to go 3.1. And then I'm going to arrange, actually maybe I'll go 3.5. And then I'm going to put them in widths of 0.5. There we go. All right. I don't think I need 0 to 40. That's the height of the bar. We can always change this later on. I'm going to go 0 to 30. That's also probably way too much. I want to make sure I don't have any equations in y equals. There's one. Clear that out. And there's my histogram. Maybe make that look a little bit better. Let me go window. I'm going to shrink that 30 down to 20. And there's my histogram. All right. Now, if I hit the trace button, and I don't think I'm going to actually try to draw this histogram out, it looks kind of normally distributed, right? If I look at this, what I find is that there's the bar that corresponds to where the 2.3 would lie, okay? So it's only the ones in here, which are very, very few, only the ones in here that are at that 2.3 or larger, all right? Not that many of the simulations had 2.3 or larger. So we could sketch out that histogram. I'm not going to do that. It would just be an approximation. I'd be kind of, putting those bars here and there. And it wouldn't exactly look like this one either, because I only made this one go all the way to negative 4, whereas mine actually went to negative 4.6. I'd actually have to extend the bar a little bit. Really, the bigger point is, if I come in here and I look at letter C, This is important. It says, look at the data list containing the sample mean differences. Given there are 100 differences, what percent of the differences were at or above the observed one? Let's go back in there and take a look at that. All right. So at or above. So I'm looking for anything at or above 2.3. Well, 2.2 is below it. 2.5, that's 1, 2, 3, 4, 5, 6. Okay, so let's go back into this now. All right, and let's fill in what's really quite relevant here. All right, we had a difference in sample means of 2.3 centimeters, which lied way out here when we had this, histogram. Oh, that's a beautiful histogram. I don't even know why I'm trying. It's like a histogram drawn by my 4-year-old son. Actually, I don't have a 4-year-old son. Drawn by my 7-year-old daughter. And my 2.3 kind of landed way out here. And what we found is only 6 of the 100 were at or above the 2.3. Okay, so, 6%, because it's 6 out of 100. Now, it says, how confident are you about the observed difference in sample means being due to induced variability and not natural variability? Justify. Well, think about this a little bit. All right, well, it all depends on what you think about as confidence, but I would say quite confident that it is due to induced variability. Only 6% of our simulations forced this difference or greater due to natural variability. So again, the idea is fairly subtle. The idea is that natural variability is just going to happen because some seeds grow more, some seeds grow less, some seeds are more healthy, more vigorous, more whatever. And if the observed differences in those means were due to sort of that random natural variability, then when we scrambled them up so they weren't in the treatment groups anymore, we would see that 2.30 centimeter difference or greater more often. We'd see it happen, 30% of the time, 40% of the time, 50% of the time. But we only see it happening 6% of the time when we sort of ignore the treatment groups altogether and we just randomly shuffle those seeds up, okay? We only see that 2.3 difference 6% of the time. So 94% of the time we're seeing something less than that due to natural variability. So I have quite a bit of confidence that the difference in sample means is due to induced variability instead of natural. Okay, pause the video now before we wrap this up. Okay, let's clear out the text. So today we looked at a classic experiment. And in a classic experiment, you randomly assign subjects to 2 or more treatment groups. They go through the experiment and you record data, right? Due to the fact that they're getting different treatments, one expects for the data to be different, right? For there to be more growth or less growth, more weight loss, less weight loss, whatever you're studying, all right? But within the groups themselves, within the treatment groups, you're going to get natural variability. You're not going to get everyone in one group loses 10 pounds and everyone in the other group loses 2 pounds, right? You're going to get natural variability. The question then becomes, how can you determine how much of the variability is due to the induced situation, i.e., the group that they were put in, versus just that natural variability? And we did that by using a simulator that mixed all the results together and then randomly divided them into groups and calculated the differences in their means. All right? And that gives us a very good sense for how likely our observed difference in means is compared to randomly generated ones. All right, well, that's pretty heavy, but that's the beginning of inferential statistics. I'd like to thank you for joining me for another Common Core Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.